The theory of relativity. What we're discussing today is the general theory of relativity in this section. The space-time curvature is basically dependent on the parameters you have around you, and what really, there are some parameters which you should pose to have a space-time coordinates change. For example, if you have some velocity, then according to space-time special theory of relativity, you have some space-time coordinate change for you. In general theory, and there are also parameters, like there are some objects around you which cause your space-time coordinates to change, and when the space-time coordinates are being changed, then the events are totally relative for you, and that's gets into the relativity in the events. Now we are in the general theory of relativity. Unlike special theory of relativity, we are discussing the parameters which get into you the space-time coordinates, but that isn't required for you to to get into some motion. There are certain objects, it's like when you get into some motion, your space-time coordinate change for you. When I say, and if I say when the space-time coordinate change for you, you get in the motion. Again, I will just repeat it again. When you get into motion, space-time coordinates change for you, and when the space-time coordinates change for you, you are in the motion. This motion is something which is mystical, right? This motion is what we call as gravity, a mystical motion. This motion isn't just because it isn't mystical, it's just the space-time curvature, but we are not moving. So what causes space-time curvature? This space-time curvature is due, that this space-time curvature due to something which we are near to, the planet Earth. Does mass bend the space-time? Does mass change the space-time curvature? Yes, it does. So it's the mass which does this, which gets into the space-time curvature, into the space-time. The space-time curvature. This when the space-time curves, you get into the motion as per the law. So this motion which you feel is gravity, which you call something which is mystical, something which we can't really see, is due to the space-time curvature caused by the mass. The mass is Earth, but it is not that easy to get the space-time to calculate. The curvature in the space-time, the fabric of space-time. For example, for masses like you and me, you're thinking like the space-time curvature is like vastly associated, that you may think it like there's some space-time curvature like ball like thing around you, which you get in a normal picture when the general theory of relativity, that there is some space-time curvature around the Earth, like there's some shallow part beneath the Earth. It's not in case of you, but though, just because the mass is too less for you to get that significant amount of curvature. So but the things like planets, stars, they have significant space-time curvature associated with them, and as there is significant space-time curvature, there is significant acceleration which we face. Even if there is so much mass in planet Earth, we are having an acceleration here with now as like 9.8 meter per second. That's the acceleration gravity which we have. And this general theory of relativity is all about that when you have something like what gets the curvature into the space-time, then the laws of the laws of physics stay constant for you, or they stay constant for you, but the events which are witnessed by two observers which are in different space-time curvature. For example, I am near Jupiter and you are near the Sirius star. So Sirius star is much heavier than Jupiter, so basically you have a stronger space-time curvature associated with you. So the same event, any event, if you witness that, it's not compulsorily what I witnessed at the same time. It may be like maybe 100 like, for example, I don't know the proper what how to calculate that, but it may like 4 to 5 years after that, when I witnessed the same event. So the general theory of relativity is all about that when you have some mass and when it gets into some space-time curvature, and how the events are relative for you. And there's some space-time coordinates, it's also accounts for time dilation. Yes, so you are on planet Earth, and you get it on the planets like Mercury, which has lesser mass than on planet Earth. Time is passes slow for you, and when you are on Mercury, not considering the gravity of the sun, the space-time curvature for you is less as compared to the planet. So there, one will see that the time is going faster for the one who is near the Mercury. And in acceleration, we had speed of light constant. In special theory of relativity, we also we had the speed of light constant, and general relativity we also have the same constant, but for that you are not a move. I mean, that constant is you. There's and it's like a constant, but there are objects in the universe broke, which has broken that constraint, and there's we have things like black holes. When you get an infinite amount of space-time curvature, my question to you guys is, what is infinity? We don't know what is infinity. When we say something which is small, how small it can be. Like, for example, if you tell me that there is some length, which is maybe which can be the short length possible, so it can be like, if I current to that length, how that is not possible because there is no length shorter than this. It's unimaginable. It's unimaginable because we don't know like how short it can be and how large it can be. We can't really comment on the events anything has, like in terms of length. So it's basically like, even you have the infinite space-time curvature, we don't know how small that particular thing is, and even space-time they can't really sustain that. And when that happens, you just cut yourself off from the universe. You no longer remain in this universe, because you have it is that's what universe does. If you violate its laws, then you are just gone out of this universe. And I don't know what's the outside universe. Maybe hyperspace, maybe some universe out there, but you're just no longer stay in this universe. The general theory of relativity is about that, like space-time curvature you have related to mass, and mass, energy, density. I would say it's not just due to the mass. In short, in conclusion, I would say it's not your conclusion even. I would like to say, in this many important things, that is the space-time curvature which you get from, like, which is described in general theory, is not only due to the mass. It's energy also. It's also the energy. It's equals to mc square, because mass is same as energy. There is space is to energy, mass, density, to be more precise. If you have like a bigger mass, a larger mass, a larger mass and less density, and space-time is like pretty much good for you. And if you have, then you can create the same space-time curvature, but space-time curvature, even if different, but you can have a much strain in the space-time by having a small mass with high density. So in general, I will say that depends on the space-time curvature, which you have, is dependent on the mass, energy, density which you have around you, and that what depends the space-time coordinates for you and the events you witness. That's the general theory of relativity. Hopes you guys have understood like what I'm trying to explain in this video, and also hope so guys understood what general theory of relativity is. If you have any question, just comment down in the comment section, and thank you for everyone to watch this video.